A program holds 1 million scores, and you ask for the score at position 600,000. Does it inspect the earlier scores first, or can it go straight there? Take a cinema row with seats numbered 0 through 7. If your ticket says seat 5, which seats must you check first? None of them, because the number already tells you the position. Replace each seat with one memory slot, and replace each person with a score. What stays the same? The slots remain side by side, and every slot keeps its numbered position, called an index. So what information lets the computer skip the search? The index. But a position alone is not a memory address, so how does index 5 become the exact place to read? The cinema row had a useful rule. Every seat had the same width, and the seats touched. What does that let us calculate? Suppose the first score begins at address 1000, and every score uses 4 bytes. Where does the next score begin? 1004, then 1008. The addresses advance by the same amount because the cells are contiguous. Seat 5 is how many cell widths from the start? 5, so its address is the start plus 5 times the item size. 1000 plus 5 times 4 equals 1020. One calculation, then one jump. Why does the first index start at 0? Index 0 means 0 cell widths from the start. Index 1 means 1 width away, and index 5 means 5 widths away. The index is an offset, not a seat count. This calculation only works while the item size stays predictable and the block stays together. That rigid shape gives us fast access, but what happens when we ask for a value instead of a position? If I ask for index 4, the computer can calculate its address. If I ask, where's the score 33, what number is missing? The index. Read index 4, and one address calculation lands on 33. To change it to 40, how many other cells must move? 0. The address stays the same, so both indexed read and indexed update are O of 1. Now find 18 without its index. Could the address formula choose a cell? No, so compare 12, then 7, 25, 9, 33, and finally 18. In the worst case, the value is last or absent, so search checks all n cells, O of n. What if we want every score? Start at index 0, read the value, increase the index, and repeat until the length. Each cell is visited once, so traversal is O of n. The same loop also performs a linear search when it stops on a match. Known index or unknown value. With a known index, read and update take O of 1. With only a value, an unsorted array may require O of n comparisons. Fast access never meant fast search. We want to record one score every day, but how many days will the program run? A fixed array asks for that answer before the first score arrives. If we know there will be 7 daily scores, a fixed array of length 7 fits exactly. Can we append an 8th score? No. The array owns 7 adjacent cells, and the memory after them may belong to something else. Why not reserve 1 million cells just in case? If we store only 7 scores, almost the entire block remains unused. A large guess avoids early growth, but it can waste a large amount of memory. What if every append creates an array that is exactly 1 cell larger? To add the 5th score, copy 4 values. To add the 6th, copy 5 more. Repeating this for n scores performs about n squared total copying. Growing by 1 solves space, but makes growth expensive. Can we keep direct access, accept an unknown number of scores, avoid a huge empty block, and avoid copying after every append? Yes, if we reserve a little extra room and grow in larger steps. Which requirement caused the problem? Fast indexed access, or not knowing the final number of scores? The unknown length. A dynamic array keeps the index layout, but manages changing capacity around it. Inside the dynamic array is a fixed backing array with 8 cells. Length counts the 4 stored values, while capacity counts all 8 reserved cells. Append 44, 50, 61, and 70. What is left? Length and capacity both become 8 with no empty cell remaining. A ninth value, 82, arrives. Can this block stretch in place? Not safely, because neighboring memory may already be used, so the dynamic array reserves a larger block and copies the 8 existing values across. Does their order change? No, they land in the same order, and 82 takes the next slot. One resize copied 8 values, so how can append be called O of 1? Count a longer run. Many appends write one cell, while only a few trigger copies of 1, 2, 4, then 8 items. Geometric growth makes the expensive events rare, so the average cost per append stays constant. That is amortized O of 1. Does extra capacity make every insertion O of 1? No. Insert 20 at index 2, and 18 shifts right, then 33, 9, and 25. Dynamic growth makes appending convenient, but preserving order after a middle insertion still takes O of n. Different languages expose this idea under different names. Python list, Java array list, C++ vector, and JavaScript array all behave like dynamic arrays for ordinary indexed storage. The exact growth factor varies, but length, capacity, copying, and amortized append are the shared model. An array and a linked list both take O of n time to visit n values. Does that mean they usually run at the same speed? No, because big O does not describe where those values sit in memory. When the processor needs score 12, it usually fetches a small block of nearby memory, not one isolated value. Which scores may already be waiting for the next loop steps? 7, 25, and 9, because they arrived in the same cache line. A linked node holds 12, but where is its next node? The pointer may lead to a distant address, then another distant address. Both traversals visit n values, yet the array often uses each fetched block fully, while the list may wait for many separate memory fetches. Cache behavior depends on the processor, item size, access pattern, and the language runtime, so this is not a new big O guarantee. It is a practical advantage. Compact sequential array traversal often uses modern hardware well. We need to store daily scores in order, read them by day number, update mistakes, search for a value, and keep adding new days. Which array costs appear in this small program? Read day 4 by index 3, and the array jumps to 9. Update it to 11 in the same cell. Find 33 by checking from the front until index 4. Append 18 at the end. Which operation moved existing scores? None, because this workload mostly uses positions and the tail. Can you predict each cost from the layout? Read or update by index is O of 1. Search is O of n. A middle insertion is O of n because later values shift. Append is amortized O of 1, and storing n values uses O of n space. Need an item by numbered position? Choose an array. Need frequent relinking when you already have the node? A linked list may fit. Need lookup by a key, such as a username? Choose a hash table. The question is not which structure is fastest, but which operation your program performs most. An array is one adjacent block of indexed values. Its address formula explains O of 1 access. Its fixed order explains O of n shifting. And geometric resizing explains amortized O of 1 append. When position matters and compact traversal is common, the simple row is usually the right place to start.